online, and I really like Pwn and Rev. Yes. Okay, so this is what we're going to be doing today. So we're first going to talk about kernel LAN versus user LAN stuff. So like fun vulnerabilities and kernel protections. Then we'll be teaching you how to do a kernel Pwn setup. And then we'll start exploiting some stuff. So we actually have an example. So it'll be kernel use after freeze and how to exploit them. Then I'll be talking about new mitigations and new techniques. Okay, so before we go into this session, everyone would probably, it will be probably good for people to have QEMU installed along with GDB Pwn debug. And if you want to follow along with the challenge, you can download the challenge files from the link that was sent in the chat. But if you just want to sit back, relax, that's fine. So just enjoy yourself and enjoy the session. Nice. Okay. So first, we're going to be talking about kernel LAN versus user LAN and what are the common vulnerabilities and protections. So firstly, what is the kernel? The kernel is basically the core of the operating system, and it facilitates interactions between hardware resources and the application layer. So in Linux, kernel operates on ring 0, which is supervisor mode, and user space operates on ring 3. Now, the thing about the kernel is that this image that you see here is an oversimplification of what the kernel actually is, because the kernel is very, very complicated. And this is about how the Linux kernel actually looks like. So there are multiple different subsystems, and every subsystem has its own things to do. And again, every subsystem will probably have their own bugs, but that'll be something we'll talk about later. So for user LAN to talk to kernel LAN, it does this via syscalls. And syscalls are a way in which they can request services from the kernel. So for example, read, write, mmac, execve, all these are done via syscalls. So as you can see, like this is a syscall table, which is basically like all the different syscalls that are present in the kernel. And the syscalls that you may know would be execve, which we see a lot in Pwn, sigreturn, which you also see a lot in Pwn, but we didn't come here for a computer science lecture, right? We want to Pwn stuff. So we'll be talking about kernel LAN Pwn versus user LAN Pwn. And the difference in this is that in kernel LAN, instead of just popping around the target, you are looking for local privilege escalation. So the exploit is usually written in C or C++ as opposed to your usual Python Pwn2 script. And the interesting thing about the kernel, I feel, is that the attack surface is very big. So in CTS, you usually see people trying to attack like vulnerable kernel modules, which are like loaded into the kernel. But in real life, people also like find kernel 0 days and try to exploit kernel n days. And these bugs are usually found in different subsystems. So for example, the perf subsystem or the NF table subsystem. And we interact with this attack surface again through syscalls. So typical vulnerability patterns still apply. So for example, in user LAN, we'll see a lot of like buffer overflows or like use after freeze. And these things are also present in the kernel. So for example, like certain 0 days that have existed, for stack-based buffer overflow, someone found a buffer overflow in NF tables, which is basically the firewalling system in the kernel. And this is another buffer overflow bug found in net. We also see heap out of bounds, which also happens in user LAN and also can happen in kernel LAN. So this is in X tables for net filter. And this is a use after free in NF tables. So all these bugs are actually exploitable and actually lead to local privilege escalation, which is very interesting. Another use after free. So this time is in some driver. And this one, you can crash the system and leak kernel information. And also race conditions. So in KSMBD, there are certain race condition bugs which can actually be exploited, which is very cool. So kernel vulnerabilities across the year. For example, in the past, we see a lot of stuff like, oh, buffer overflows and whatnot. But now we're seeing less buffer overflows and we're trending towards different kinds of bugs. The common ones that we usually see are use after freeze, race conditions, out of bounds writes, and also ref count errors. So let's talk about some protections. So in user LAN, we have checksec, and checksec will tell us if certain protections are enabled or not. So for example, the stack can have a stack canary, there can be NX, there can be ASLR, there can be full real row and stuff like that. So in user LAN, these are the protections that we see. But in kernel LAN, there are different protections, but they are quite similar. So there's KASLR, which is kernel ASLR. SMEP, SMAP, which we'll talk about, KPTI, and many, many more. So we'll first talk about some kernel land protections, and these are the common ones. So there's KASLR, which is the normal kernel ASLR. So it's just ASL for the kernel. And it randomizes where the kernel code is loaded at boot time. There's also a special kind of KASLR, which is called FGKSLR. And instead of like the entire kernel code being randomized together, different functions get randomized on their own. So the offsets become really weird and annoying, and they change with every boot. But this can still be bypassed because some functions are not affected and the kernel symbol table location is not affected. So for example, in FGKSLR, the symbols that are pointed to in green, these are unaffected by FGKSLR, but the red ones, which are the important ones that we care about, like prepare kernel cred or commit creds, these are affected by FGKSLR, which is very annoying. So we also have SMEP, and SMEP is basically like NX for the kernel. And this marks all userland pages as not executable. And the purpose of this is basically to prevent read to user attacks, but this can be bypassed with a ROP chain, so this is not very annoying. Similarly, we have SMAP, which marks all userland pages as not accessible. So this also prevents read to user attacks, but we don't really care because we are going to use ROP anyway. And there's KPTI, which basically separates user space and kernel space page tables. So this is introduced to prevent meltdown. And there are two sets of page tables. So basically there's supervisor mode, which is basically like kernel LAN. And this includes both the kernel and user addresses. But for the user LAN page tables, they only include the user LAN addresses with a minimal set of kernel addresses. So this is bypassed using the KPTI trampoline, but we'll be talking about this later. So part 2, we are going to do a kernel pwn setup. So before we can go about starting to exploit and find vulnerabilities, we need to actually have something that we can use to debug the kernel as we go along. So this is where your QEMU actually becomes very useful. So first we talk about the different files that are usually given to us in a kernel challenge. So usually there will be a BZ image, which is like a compressed VM Linux. So they can either give you BZ image or VM Linux. Then sometimes they'll give you like module.ko, which is basically the compiled Linux kernel module that's loaded into the thing when it's running. Then there will usually be a file system. So in this case, I gave you guys an init ramfs file system. There's also usually a run script for you to start QEMU. And the run script usually tells you what kind of protections are enabled. And usually people like to include a config file. So the config file also tells you what protections are enabled. So a run.sh usually looks like this. And the things highlighted in blue are actually the protections that are enabled for a certain like challenge. So in this challenge, there's SMEP, SMAP, KASLR, and KPTI. But you see, when we run this is not very useful because this gives us a user shell and not a root shell. And the thing about a user shell is that you don't have access to a lot of interesting information. Like for example, the proc telsims file, which has the symbols and all the addresses that the symbols correspond to. Like that is not accessible by not the root user. So this is not very helpful for debugging. So what we want to do is we want to have a debugging setup where we are the root user so that we are able to like further develop our exploit. So first we'll unzip this file system using like some sort of unzip script. So this is just what I use, but honestly anything will work. And then we will modify the init tab. So there's this etc init tab file. And usually you'll see like this line that says set UID GID and then like 1000, but that will be a normal user account. So what we want to do is we want to change 1000 to 0, and 0 will be the root account. Then we will rezip the entire file system using some script that looks like this. And then we'll run it again. And after we run the run.sh again, we'll have a root shell, and this is very good. But where are we going to go from here? So we are going to slightly modify run.sh into debug.sh, where we add some new stuff in it. So first we add this small s and this big S, and basically this allows us to attach GDB to this thing remotely, and it will wait until GDB issues a continue command before it actually starts booting the kernel. And secondly, we're going to turn off KASLR. And this is just so that it's easier to debug our exploit before actually like trying to run the exploit on a real system. Now, this doesn't mean that when we develop our exploit, we assume that there is no ASLR. We do write our exploit with the thought that ASLR is still there. So another thing that I like to do is if I'm given a BZ image file, I will extract this to VM Linux just so that it's nicer to debug. So after that, what you can do is attach GDB. So you just do GDB VM Linux tar rem1234, which is basically like attaching your GDB to like a remote debugging setup, and then you hit C. So this is usually the setup that I use to debug. So I have the debugger on the left and the QEMU screen on the right. And when the entire thing is set up, it looks something like this. So on the left, we actually have the debugger, and we can actually see that, oh, the debugger is running and is connected to the kernel instance. And on the right side, there is a root shell for us to do whatever we want. So at this stage, we are ready to start looking at source code and getting ready to debug. But there's one more thing I'd like to tell you guys. So just now I mentioned the proc calsims file. So this is the proc calsims file. And basically, as you can see, there are a lot of very interesting addresses which are very useful. And also it has all the symbols. And this is just generally good because then we can set breakpoints and stuff depending on like what the addresses are. Okay, finally we've arrived here. So this is, I'm going to talk about kernel use after freeze, especially in the heap. And this is where the fun begins. So just a little bit of backstory. One day, I was talking to my friend about Pwn, and I was like, what happens if I allocate a buffer that's larger than all available memory? And he sent me this. And he was like, okay, what, we malloc it all? And I thought it would be funny to write a CTF challenge where the bug was basically triggered if you allocate a stupidly huge amount of memory. So for example, if you allocate like the entire memory, like what happens if you just allocate all the memory and something bad happens? And the thing is, you see, like I studied chemistry, and of course, being a chemistry student, I had to write a challenge that was related to chemistry. So this is when chem inventory comes into play. So the challenge goes, storing explosive chemicals in the kernel is a wonderful idea. Surely nothing can go wrong, right? So actually, fun fact about chem inventory is a real system. We actually use this to catalog chemicals in our lab. And yeah, basically this just keeps track of what we have and where they're stored, which I think is quite fun that we can do this in the kernel. So if you look into the files that are given, one of them is cheminventory.c, and that is the source code for the kernel module. So in the source code, you'll see these 4 do operations. So do create, do replace, do read, and do delete. And basically, these are the different IOCTL, functions that we can use. So you can talk to the module using IOCTL, and it takes in this rec structure. So rec, I just called it rec, but it's like request. So it takes in this request structure from userlet, and then it will use the information from this structure to do different operations. So all the operations from this module operate on a chemical structure. And the chemical structure in this case in the module is 256 bytes. So just a fun fact about chemicals, but in the structure, you see that there is a CAS number, and this is a real thing. And a CAS number is a unique number assigned to any chemical it's like an identifier. So for example, guanosine's CAS number is 118003. Yes, just something fun. So let's go into the details of the different operations that you can do. So the first one would be do create. So using the rec structure that we have previously here, you can see it takes in quantity, a CAS number, the index, a node size, node address, and a name address. So basically, like what it does is it will take that information and create a chemical structure from it. It will first allocate a new chemical structure with the GFE kernel flag. We'll explain this later. And then it will ask you to fill in the quantity, the CAS number, and then it will be assigned an IDX number. So it will be assigned an index number. This is very important later on. Afterwards, this chemical structure is linked into a linked list using a list at tail. So the head of the list is chemical head, and it's just going to be linked into that. So after that, there'll be this node thing going on. So it will create a node using kmalloc, and it will allocate it in GFP kernel account. And then after that, it will just like fill in like all the information. So basically do create is just a very simple like create node kind of function, and it creates a chemical object. So more interestingly, we have do replace, and this is actually the buggy function. So if you see the top, it will first check if the user provided a node size that's equal to 0. And if the node size is 0, then the function will fail. But if not, what it will do is it will walk the chemical linked list. So remember we struck chemical into a linked list just now when we created it. It will walk that linked list, and it will compare the provided requested index number with the index number of all the chemicals in the list. And if one matches up, that chemical will basically be replaced. So you're trying to replace an item with a linked list with a new one. Okay, so let's go through this in greater depth. First, we will find the chemical object with the matching index, and then we'll free that object. Afterwards, we create a new chemical object, and then we link it into the linked list. So note that once this object is allocated, it will be immediately linked into the linked list, even though the node has not been created. So afterwards, we will allocate a new node for this chemical in accordance to the size that we requested. So for example, if I requested a size that's like 20, then it will kmalloc 20, and then that will be considered the node for that object. This sounds like a terrible idea because remember in do create, it will check the node size. So for example, if the node size is greater than 100, or if it's equal to 0, it will just fail. Like the node can only have a size between 0 and 100 bytes. The problem with do replace is that it only checks if node size is equal to 0, but it does not have an upper bound for the node size. So this means that, remember that when we have do replace, the new chemical object is already linked into the linked list, even though we haven't created the node object. So somehow, if we can get kmalloc to fail and return null, we'll get a use after free. Because what happens is if node equals to null, it will free the chemical object, even though it's already linked to the linked list. So this is a bug, and this can be potentially very, very bad because the free object will already be in the linked list, and we can access the object using the IDX count. So this is buggy. So let's talk about kmalloc first. So kmalloc basically allocates memory. That's what it does. And the way it allocates memory is based on the size and the flags that are provided. But first, let's talk about the return value. So if kmalloc succeeds, it would return a pointer to the allocated memory region. And if it fails, there are two scenarios where it fails. So one is if you try to kmalloc 0, it'll give you a 0 size pointer, which is not very fun. And it can also return null. And null happens is when kmalloc fails, but there's insufficient memory available to be allocated. So if we allocate a stupidly large amount of memory, kmalloc will just combust and fail and return null. And this will give us our use after free. So this is the bug in this challenge. So let's finish our source code analysis before we go on to exploitation. So there are two other functions. One of them is do read. And basically, right, it will walk the linked list and see if the provided IDX from the user is same as the chemical IDX. And if it is the same, it will return the chemical's name and the information in the chemical's node back to the user. So this is just like a normal read function. This is very useful later. And lastly, in do delete, it's also very similar. So it will compare the user provided index value with the chemical's IDX value. And if they are the same, it will just delete that chemical from the linked list. So it will do a list delete. This is very important later. And then it will free the object. Yep. Okay, so we have found the vulnerability. Now what we need to do is we need to develop a plan on exploiting this vulnerability. So next step would be to get a kernel text dig, because ultimately we want to construct a ROP chain. And we know that there is KSLR. And because there is KASLR, we need to have a text leak so we can calculate offsets. Okay. So first, we have to talk about kernel protections. We don't just have the normal KASLR, SMEP, SMAP, and KPTI in this kernel. This kernel is actually increasingly terribly hardened in the sense that it has all these other protections on it. We will go through these protections one by one, but first we'll talk about config memcg kmem. So basically what this does is that, sorry, let me just get some water. Okay, so basically what this does is that, remember I told you that kmalloc allocates objects based on size and its allocation flags. Now, this will have an impact on which cache the object is allocated in. So for objects with GFP kernel as the flag, it will be allocated in a normal kmalloc cache. So for example, if an object is 16 bytes in size and is allocated with GFP kernel, it will go into kmalloc 16. But if an object has a GFP kernel account flag, it will be in a completely different cache from an object that does not have the account on it. So this is actually for untrusted allocations triggered from user space. And for example, if I do like kmalloc 32 GFP account, my object will end up in kmalloc CG32. Yeah. So this means that we will have some issues trying to deal with the chemical object because struct chemical is of a size of 256 and is allocated with GFP kernel. So this means that it will end up in kmalloc 256 cache. So again, this is the structure of struct chemical. And we can see that from this is 256 in size. So we'll first talk about how to obtain a kernel text leak. So usually the way to do this is that we want to reclaim the free space from the victim by allocating another kernel object, and then we will read from that object. So the challenge lies in finding the right object to use. And the object must be allocated in kmalloc 256, or it will never be able to replace that object because it's allocated in a completely different cache. And remember when we were talking about do read, we said that index value has to be valid. And this is because when you walk the linked list to determine which chemical object to operate on, it will check the index value. So we'll talk about the next protection. This one is not very annoying, but this is something that's enabled in most kernel distributions now and most kernel challenges. So this comes as a set. We have config slab freelist harden and config slab freelist random. So freelist harden is basically consecutive double free protection. So if I try to trigger a double free directly after each other, it will just fail. The kernel will just panic and die. And this is to prevent freelist poisoning attacks. So another thing that it does is that pointers in the free list are obfuscated by XORing the pointer with a per cache random number and the address where the pointer is stored. So this is actually from the kernel source code, and we can actually see how this is implemented. So unlike your typical like nice key cache poisoning attack, like because it like XORs it with a random number, this is just very annoying to exploit, and most people just don't really bother with this. So there's also config slab freelist random, which is basically the allocation of memory chunks being randomized based on a per cache random sequence. And this is basically to make sure that chunks are not allocated directly one after another. And this is to protect against kernel heap overflows. However, in this case, we don't really have a heap overflow, so this is not very annoying to us. So with all the mitigations that we are talking about, we have to talk about heap spraying. So heap spray is basically a technique used to control the memory layer of the heap. And if we spray enough objects, one of them will eventually reclaim the space occupied by our freed victim object. This is usually done by calling a certain syscall a lot of times. So remember that we talked about the allocator, and the object we want to use to reclaim the victim object must be allocated in the same cache as our victim object. So in this case, we will be using something called timer FD-CTX, and this is allocated in kmalloc 256. So why is this interesting? If we are able to arm our timers, we are able to get a kernel text leak because there are some very interesting pointers in that structure. So this is actually how the timer FD-CTX structure looks like. So in order to spray timer fd ctx, all you need to do is call timer fd create and then arm the timer by timer fd set time. And after we do this, basically it will just create a lot of different timer fd ctx objects. And hopefully one of them will occupy the space left by the victim object. So remember that I said when we do a do read, the index value has to be valid. And that is because when we choose which chemical object to operate on, we will walk the linked list to compare the IDX value until we have the same one. And this is really good because timer fd ctx, the area with the index value in the original chemical structure is 0 in timer fd ctx. So we can treat this as the timer fd ctx having an IDX that is 0. So this will give us a valid object. So all we need to do is, if we want to read from this object, we can call doRead to read the kernel text. And this is brilliant because remember that in our chemical object, we have 0xC8 characters in the name object, and we are able to read data from this using doRead. And you can see that here we have some very interesting pointers. And this would be the source of our kernel text leak. Or rather specifically, this would be the pointer that we are interested in leaking. Okay, great. So for heap spraying, there are actually other objects that we are going to look at. So some very common useful objects that we have. So for example, there's kmalloc cg32, which gives us RIP control and a kernel text leak, which is nice, and it's very easy to spray by just opening proc self-stat. So this is the sec operations struct. So this is how it looks like. We also have file. So file is just allocated by opening a file. It can give us RIP control and a text leak. And this is allocated in the flip cache, which is slightly more annoying. We'll talk about that later. We also have tty struct, which is allocated in kmalloc 1024, but it actually is very useful because it gives us RIP control, a text, and a heap leak. And you can allocate it by opening dev ptmx. Another object which I like a lot is pipe buffer. So this is allocated by opening and writing to a pipe. And actually, the pipe buffer structure is very small, but they're allocated as a ring of pipe buffer structs. So they end up in kmalloc cg1024, which is very useful. And this will give us RIP control and a kernel text leak. So there are also objects which are dynamic objects. And what this means is that it allows us to basically choose the size of the object that we want. So for example, for message, we are able to allocate an object of multiple different sizes, anywhere from kmalloc cg64 to kmalloc cg4k. So this is very useful because if we have a victim object in any one of those caches, it is very, very powerful. So this is very useful for getting a heap leak. And also, most people like to use this for forging a kernel structure. And that is because, so the struct MSG header is like this, but right after the header is like completely controlled by the user. So you can actually completely control anything here. And this can be used to like make fake structures and stuff, which are useful for exploits. So this is allocated via message get and message send. Okay, so a few things I want to talk about this structure. So first, instruct list head. So this M list thing, the message objects are basically sent in something called a message queue. And the list head struct is basically like pointing to the next and previous objects of message objects in the queue. But there's also a struct message stack. And this is basically an object that's allocated when you have a message that is very big and cannot be contained in one page. So you allocate an extra object as like a continuation of the same message. So to reiterate that again, like mlist will basically be messages in the same queue, and message stack is basically like the data but of the same message object. So this is how message stack looks like. This can be allocated in CG16 to CG4K, and similarly very good for heap leak and very good for forging kernel structures. So this is allocated when the size of the system v message is actually greater than the page size, which is 4096 or 0x1000. And the very nice thing about this struct is that the header is only 8 bytes because it's just a pointer, it's just a message 6 next pointer. And after that, it's completely controlled by the user. So this is a very, very powerful object. So there is another object that I want to talk about, and this is a non-VMA name. And honestly, I just included this because I thought it was very funny. But basically what this does is that if you have any data that's written to a specific memory region via a race condition, this can be read off the prop PID maps file. So a non-VMA name is basically like the name object of like anonymous memory regions. And if any information is written to this object, it will appear in the prop PID maps file, which I think is very funny. So the size of this object can be kmalloc 8 to kmalloc 96. And this is actually a picture of the prop PID maps file when you have something that's written to it. Okay, so what do we know so far? We know that we can trigger the UAF vulnerability. We can create a chemical object. We can cause a UAF by replacing the object by allocating a stupidly large amount of memory, which will cause kmalloc to fail and for the object to be freed. We can reclaim this object using timer FD-CTX to get a kernel text leak. But in order to progress, we want to get more control of this victim object. We need to reclaim the victim object with a dynamic object so that we can forge structures. We can basically mess with stuff inside this chemical object to further exploitation and get RIP control. Now the problem is, remember I mentioned the whole thing about objects being in different caches. Our nice dynamic objects like message, these are in the wrong cache because message is allocated in kmalloc CG compared to the chemical object which is allocated in kmalloc 256. So this is a problem. Enter the cross-cache attack. So basically, the objective of a cross-cache is to make the kernel reallocate the slab with our victim object from its original cache to another cache where the target is allocated. So in order for the kernel to allocate a new slab to a particular cache, the following needs to be fulfilled. So firstly, the cache free list must be empty, then the page free list must be empty, then the CPU partial list must be empty, then the node free list must be empty. So in short, if we spray enough of our target object, we can exhaust all the free lists and force the kernel to allocate a new slab to the target object cache. So how do we allocate a slab that has our victim object to the target object's cache? So for example, our victim object is a chemical object which has 256 bytes of size. So that will be in kmalloc 256. But the message object that we want to use is kmalloc CG256. So we want to reallocate the slab originally with the chemical object in kmalloc 256 to a kmalloc CG256. So now this is done by fulfilling these two conditions. So firstly, the CPU partial list must be full, and this will trigger a call to unfreeze partials. Secondly, the slab must absolutely have absolutely nothing on it. There must be 0 allocated objects on it. And only if the slab is completely free will a call be made to free slab, which will give us the ability to allocate a free slab to any cache that we want. So we are going to combine the cross-cache attack with the kernel text leak so that our upcoming exploit steps would be easier. Also, we think. So this is a really nice diagram by Rao and PQL, and this basically shows how like the whole slab thing works. So as we can see here, like we can only get unfreeze partials if the partial list is full. And if the slab itself is empty, then we can reach free slab, which is basically the goal of the cross-cache attack. So there is a proper way to cross-cache, and this is covered really well by these guys, but I'll be teaching you the lazy way to cross-cache. So firstly, you want to spray a timer FD padding spray. So you want to try to get the kernel to allocate a new slab to you so that on the slab, there's absolutely nothing other than timer FD CTX objects and free objects. So this is how the slab will look after the padding spray. So remember that the objects are not directly allocated one after another, and this is because of the free list randomization. Next, we are going to allocate the victim object. So in this case, we'll create a chemical object using some IOCTL. So I just called it create chem and I made a function. Oops. So this will basically take out one of the free spots and allocate our chemical object into that same slab. Next, we want to trigger the vulnerability. So we are going to replace the chemical object, but we are going to cause replace to fail by using a very stupidly huge amount of memory for the node object. And this will prematurely free the victim object, giving us a free spot. So after that, we are going to reclaim the victim object. We are going to spray the slab with TimerFT CTX objects. And now the slab will be full of the TimerFT CTX objects, and they will look like this. So next, before we do anything, remember we need to perform a kernel text leak because we do need to calculate the kernel base so that we are able to do our ROP chain. So we need to read from the victim object via do read IOCTL. And remember, because IDX was 0 from TimerFT, we are actually able to leak memory from this object. Afterwards, once we have gotten our leak, we are going to free all the TimerFT CTX objects. And remember, this was a necessary condition for the cross-cache to work because the entire slab has to be completely free before we can perform a cross-cache attack. So this will involve us freeing both our spray afterwards and also our padding spray. Now, finally, what we're going to do is that we are going to spray the entire slab with message. And we'll be using total size 256 so that it will get reallocated to kmalloc CG256. So at this point of time, the entire slab has been reallocated and the victim object has been reclaimed by a message object, which is originally supposed to be allocated in a different cache. But due to the magic of the cross-cache attack, we are able to allocate that object onto the victim object. So currently, this is how our exploit looks like. We have performed a kernel text leak. We have gotten the kernel base, and now we have replaced the victim object with a message object that we can use to further forge structures to further help our attacks. Okay, I think we will take a 2-minute break. Just so if anyone has any questions, you can ask the questions, and we'll be back in, okay, let's do 9:45. Does anyone have any questions? Yeah, the slides will be, I'll post the slides later, yes. How do you know which objects lands in which cache? So basically, to determine what object will land in what cache, if it's a kernel object, basically you need to go to the kernel source code, and after that you need to see like how the object is allocated. So first determine the size of the object and then check the flags that they use for kmalloc and whether it's Jeffy account or Jeffy kernel. And if it's Jeffy kernel, then you just check the size of the object and then it will just be kmalloc that size. Yeah, so if it's a weird size like 60, then it will go into 64. So it will be a size that can fit the object, but the smallest one possible. Yeah, so if it's Jeffy kernel account, then it will go into kmalloc CG something. Yeah, so that's how you figure out what object goes into what cache. Okay, so let's continue. So currently at this point, we have our kernel text leak, and we have basically reallocated our victim object to a message object. And now from there, we need to transform our UAF primitive to something that will allow us to eventually control RIP. So Let's just take a look back at the chemical object and see what we can use to help in our exploit. So first, we know that we can read data from this object via the name portion, but there's also something else that's very interesting. And the doRead function actually allows us to read data that's pointed to by this node address. So if we are able to put a fake pointer here, like to wherever we want to read, we can get arbitrary read. So that is very useful. Another thing that is very, very interesting is that we can mess with the linked list via do delete. And basically, we can create like fake linked list objects, which will be very interesting. So as long as IDX is valid, we are able to free any object in the linked list. So in the sense, we have arbitrary free, kind of. Let's just first talk about unlinking an object. So this is actually how a linked list would look if there are like 3 chemical objects, so 0, 1, and 2. So I'm just gonna omit the arrows to chemical heap previous and chemical 2 next because it's quite confusing. So for example, let's say we want to unlink chemical 1. So chemical 1 next, it will be written to chemical 0 next. So this will go to that. And chemical 1 prev will be written to chemical 2 prev. So this will go to that. And afterwards, we will remove this object and the linked list will look like this. So that is how a normal unlinking will look like. So there's this live overflow video about a very famous exploit, first published on Frag, about the DL malloc unlinking exploit. And maybe we could have a similar idea where we basically use this unlinking mechanism to gain some sort of arbitrary right to an address that we want. So we know that we can control both next and prev if we have our victim object point to like a message object, which we control. And we do know that the following rights are possible. So we know that next prev will be equals to prev and prev next will be equals to next. So what if next prev was the location of mod probe path and prev was bin/sh? And if we are able to override mod probe path, so this is actually a very common kernel exploit technique, but basically you override mod probe path and run an unknown file. You run an unknown file and basically it's supposed to call that to resolve like what kind of file it is. But if it points to bin/sh, it will just give you a shell, which is exactly what we want. And since this is a kernel exploit, hopefully it will give us a root shell. But you see, yeah, that's probably not going to work because we have config static user mode helper, which means that we are not allowed to do a mod probe path override. So the kernel will only execute a single user mode binary defined by config static user mode helper path, and mod probe path becomes read only, which means that this DL malloc style unlinking attack where we write the mod probe path will fail. So this is not going to work. Cue screaming cat. So the proposed attack plan is that what if we make the victim object point to like a fake chemical object in some cache that we want, and then we free that object. So technically, because we have arbitrary free, this will give us a double free, right? No. Basically, what happens is the kernel will bug out and complain, and it will basically stop your exploit from running, making you very sad. And if you notice what happens, if it fails here, it fails on do list delete entry valid or report, and it fails there because one of the list checks have failed. And this is because of config list hardened, which is a list protection. So basically, if you look at the kernel source code for list delete, and because we have config debug list on, it will go to this list delete entry valid or report function. So certain conditions must be met before we can delete and unlink an object from a linked list. So for example, next cannot be null, prev cannot be null, next cannot be list poison, prev cannot be list poison. So these two are more interesting. So prev next and next prev must be proper values. So in this case, we see that prev next points to our object that we want, but next prev actually doesn't point to anything that's what it's supposed to point to, and that will fail. And because this fails, the kernel will be like, okay, this unlink is corrupted, we are going to stop this exploit from running, and your exploit will fail. Oh no, what do we do now? So instead of doing that, we are going to do something called making a fake linked list. So technically, I realized that you can do this with one less object if you need chemical hit, but I forgot to do so. So let's just do it this way. So basically, we can have a fake linked list, which is actually valid, but it's made up of objects that we control. And we know that message is powerful. And because message is powerful, we can control the things that are inside it and make it in a way so that we are able to make it seem that the list is valid. So remember that I said that in message, you can have different messages in a queue. And the messages in the queue will be related to each other via the list head mlist. So instead of just spraying one message, what we are going to do is we're going to spray a message in kmalloc cg256 to reclaim the victim object. But we're going to spray multiple other objects as well. So we have fake object 1, something I call the target object or secondary message, which is actually the target of our free, and I'll explain why later. We're going to have fake object 2 and fake object 3. And so what we want to do is we want to leak the addresses of all these fake objects, because these will be the fake objects that we use to construct the linked list. So firstly, I'm just going to show you how to spray message. So what you're going to do is just do message send and then put the thing inside. So this will be the victim object. This will be the fake object 1. The secondary message, which is our target message object in kmalloc cg1k, fake object 2, and fake object 3. So remember that I said that we can leak data from the name via do read, and we can leak data and node address via do read as well, but that will be an arbitrary read. So we're going to exploit this function of the chemical object to basically get a read on all the object addresses that we want. So first things first, what we're going to do is we are going to read name from chemical to leak the list head next and list head pre pointers from our victim object message, because this will point to fake object 1, and we want the address of all the objects that we have here. So after we have done a do read on this object, what we're going to do is we are going to free the victim object, and we're going to spray a new message object in kmalloc cg256. But in this time, we have no address being the address of fake object 1. So no address gives us an arbitrary read, and this allows us to read the list head next of fake object 1, which points to a secondary message or target object. So we're going to do the same thing with all the other objects, basically freeing and respraying the victim object to basically walk down this linked list. And by walking down this linked list, we are able to leak the addresses of all these objects, which we will be able to use to chain together our fake linked list. So similarly, do it with secondary message, do it with fake object 2, and we have all the addresses that we need. So this is actually how it looks like in the exploit. So we first do a do read, and we read from the chemical object to give us fake object 1. We free the message and spray a new message, but this time with no address pointing to something that we want to read from. At this point of time, we have all the leaks that we need. It's time to construct the fake linked list. And this is how the exploit looks like when it's run. So this is what we are looking to create. And basically, in all of the message objects, we have this list head objects that will basically chain together to form a fake linked list, which is valid. And in this case, we see that we have fake object 2. And fake object 2 is a valid object in a valid linked list, which passes all the list protection checks. So this is the object that we want to free. But remember, when we free a chemical object, we also free whatever is pointed to by no address. So what we're going to do is we're going to have no address pointing to a target object that we want. So in this case, we have it pointing to a kmalloc cg1k object that has been filled with a pipe buffer object. And I'll explain why this is useful later. So I'm just going to show you how the fake linked list looks first. So this is how it looks like in the exploit. It's just respraying different message objects. So we've done a kernel heap lead. And now we're going to go to RIP control. So remember I was talking about the fake linked list. If we free the fake object 2, we also free the target object. So let's do a free. We've freed this object, passes all the link protection checks, and we have freed this pipe buffer object at the same time. The thing is, the pipe buffer object is allocated with a valid pipe buffer object. So in a sense that we have a double free, because we can actually spray something over this allocated pipe buffer object. And this will give us a lot of control for different interesting things that we want to do later. So let's take a look at pipe buffer first. Pipe buffer has this very interesting thing called pipe buff operations. And let's take a look at what pipe buff operations does. So pipe buff operations is basically like a bunch of pointers to different functions. And more interestingly, there's pipe buff release. And this is really, really interesting because when we close a pipe buffer object, it will call release and run whatever function that is pointing to. So how are we going to control RIP? We are first going to spray something over the freed pipe buffer object. So what I was going to do is I am just going to spray like a fake pipe buffer object. But in this case, I'm going to override pipe buff ops, which will point to something that has a fake pipe buff release. And the release will be basically the gadget kicking off our ROP chain. And it's very easy to trigger the RIP control because all we need to do is close all the pipes and that will trigger release. So basically, that is our RIP control, but we need to discuss how to get root. So the thing about kernel exploits is usually we have to do a stack pivot because a lot of our addresses and stuff that we are dealing with, like currently our payload, our ROP chain is in the heap. So what I like to do is I'll let it crash at like some fake address like Dead Beef Cafe Babe, which is what I usually use. And I'll look at the different addresses inside the registers. So in this case, RDX and RSI point to basically an object in the same cache. And that is the target cache, which is kmalloc cg1k. And kmalloc cg1k has our ROP chain. So we're going to explain how to do a ROP chain. And the thing is, before doing any kernel ROP, I will say that when writing a kernel ROP chain, you need to be very careful that the gadgets are actually executable. Because when you run a ROP gadget on like VM Linux, you get a lot of gadgets and it looks really nice, but some gadgets are in non-executable regions. So just check your gadgets to make sure that they are real gadgets before proceeding. So kernel ROP is very interesting because first you need to do a stack pivot. And the way I like to do a stack pivot is by using a drop gadget. So a drop gadget is a jump-oriented programming gadget. Remember, RSI has an address of the heap which contains our ROP chain. So what we're going to do is we're trying to get RSI into RSP. I'm going to push RSI onto the stack. And then I will jump to keyword pointer RSI x039, which I control. So this will jump to this gadget here. And this gadget is basically a pop RSP gadget. Now the thing on the top of our stack right now is the value of RSI. And that is a value which is basically pointing to a kmalloc cg1k address. So basically, by doing these two steps, we are able to pivot the stack to where we want it to be. Now, usually after this, what I like to do is I like to just do a very big red, like red 100. And the reason for this is so that I don't corrupt anything that is important on the like area that I write my ROP chain to, because there may be other fake structures that I have like created on it. So the goal of a kernel ROP is to call commit creds on prepare kernel cred, which is called on init task. And the reason for this is basically you want to make a new cred as the root user and then just use that. So when you return to user land, you are root instead of a user, which will give you privilege escalation and which would basically solve the challenge for you. So prepare kernel cred. This one is quite easy. Basically just find any gadget that lets you control RDI, pop init task into RDI, which you can calculate from kernel base, and then just call prepare kernel cred. This is quite simple. the annoying part is after prepare kernel cred returns, it basically puts wherever you want into RAX, but you need to get that into RDI because you need to call commit cred. So the way I like to do this is by a drop again. So what I'm going to do is, in this case, my drop gadget is push RAX jump keyword pointer RCX, right? So I first put what I want into RCX here. So for example, this Heap 1024 plus 0x7178, this is actually this, which is my next gadget. And then I'll do a push RAX, which will push the value from prepare kernel cred onto the stack. And then I will do a drop. So now this will jump here, and this will call pop RDI. But the thing is that whatever was originally in RAX will be on the top of the stack, which will then be popped into RDI, leaving the stack intact and giving us what we want. This will then be wonderful because after that, we can directly call commit creds with the stuff that we want in RDI. Great, we're almost done. So after that, we are going to return to user space. And this is done quite simply. So what we're going to do is first, we're going to swap the GS register between kernel and user mode. So this is done via the swap GS. You can also do this with the KPTI trampoline. And after that, I'm going to call IREDQ, which will basically return to user LAN. Now, IREDQ is going to need some registers from us. So it'll be user RIP, which is where we want it to go. Usually, I define like a get shell function and use that as user RIP. Then we have all the other registers. So user CS, RFlags, SP, and SS, which we save the state originally here. So after we return to user LAN, sometimes the exploit will be a bit annoying and it will seg fault in user space. So what I like to do is I'll just call a signal handler because anyway we are root. So what happens is on seg fault, just pop a shell. And even if it's seg faults, it'll give me a root shell, which is nice. So get shell actually looks like this. So it'll just call bin/sh and give us a root shell, which is nice. So demo time. Yes, so you can see after running the exploit, we have a root user, which is basically our goal for kernel exploits. Yep. So finally, after all of this work, we have a root shell. And basically, we have solved one kernel phone challenge. Now, the thing is, like, that was a kernel CTF challenge. And CTF challenges are intentionally vulnerable. And the thing is, most CTF challenges don't actually use the worst, most updated, annoying mitigations that exist. So for example, something that has been coming up quite a bit, in fact, I've seen this in a CTF challenge, is config random kmalloc caches. And basically, this is to mess with your heap spray. Because instead of just having one cache, like for example, kmalloc CG256, there will be 16 kmalloc CG256 slab caches. So there'll be 16 caches for each size. And when an object is allocated, it will go into one of the 16 caches, but you don't know which one. And this is because this depends on where kmalloc is called and a per boot generated seed. So this is hopefully very unpredictable. And this also means that our heap spray will be distributed across 16 different slab caches, which is really annoying. So far, I've realized that the solution to this is just to increase the size of the heap spray, and hopefully this will improve exploit stability. But yeah, so this is just something that is meant to thwart heap spraying attacks by decreasing the reliability of exploits. Now, something that would prove a bit more annoying would be this. So there was a post last year on one of the Linux mailing lists saying cross cache is dead. And because now there is config slab virtual. So this is a mitigation for the slab allocator that prevents reuse of virtual addresses across different slab caches. And basically, because you cannot cross cache, whatever I have shown you before with the chemical object being replaced with a message, that will no longer work. because the step caches cannot be allocated to the different slabs cannot be allocated to different caches. So this will just complicate exploitation a lot. So in this case, your heap spray object will have to be in the same cache as your victim object, which is quite annoying. So this is currently not enabled for most default Linux distributions, but yeah, this is up and coming. The other thing that's actually quite interesting is the kernel has now have support for Rust, and this was introduced in kernel version 6.1. So the idea is to have memory safety actually bolted into the kernel as opposed to like an afterthought. So we are hoping to see more memory safe stuff. But as to whether this will improve the like lack of exploitability of the kernel is yet to be seen. But the thing is, with new mitigations, we also have new techniques by wonderful researchers. So that I think 2 or 3 years ago, there was dirty cred. And basically this is trying to free an unprivileged credential and allocate a privileged credential, which will allow you to operate as a privileged user. So in this case, you are able to write to etc password, which is really fun because then you can just create a new, like, you can change the root password to like something that you know and instantly get root access. So this is by Zhenpeng Lin. Yes, there's also a dirty pipe. So this is CV20220847. And this was actually discovered by Max Cleverman when trying to debug something. And this is similar to Dirty Cow, but this is very easy to exploit, which is very nice. So how this works is that there's this pipe buff flag can merge flag, and this basically allows you to write to a certain file if you splice data. So this can also give you some sort of like arbitrary write to any file that you want. And honestly, the chem inventory challenge, so that actually can be solved by dirty pipe. So if you leak the pipe buffer object, and you write the pipe buff flag can merge flag in, you can possibly get an arbitrary write to any file that you want, which is really nice because then you don't have to use a ROP chain, and hopefully the exploit will work on multiple different kernel versions. More new techniques. We also have UMSA, which is user space mapping attack, which is basically an attack that lets you patch the kernel code. So you can patch certain syscalls, which is very fun. Apparently this can break CFI. We also have dirty page table, which is also a database exploitation technique. And this also allows you to basically patch the kernel code, which is very cool. So this is actually seen in the CTF challenge. This was seen in MoCon Final 2023. Yeah, very interesting challenge called K-Easy. Pointer Udai has a very good write-up about this. And recently, I think it's like late last year, there's this technique called Red Spill by Arizona State University, where they basically employ user data already on the kernel stack and use that for privilege escalation. So this is a very cool technique. So kernel exploit pipeline for 0 days and not 0 days. So generally people have to find the bug. And then that's one monster of itself because finding a kernel bug is very, very difficult. There are a lot of people trying to find kernel bugs, and I think the people developing the kernel have also become like very aware of this and write the most secure code that they can. The next step would be to figure out how to trigger the bug. And this is actually harder than it sounds because maybe for CTF challenges, it's just an IOCTL in a Linux kernel module that someone wrote. But in real life, a lot of these bugs pertain to like actual subsystems. So for example, like NF tables or perf or like KSMBD. And usually these subsystems are very, very complicated with many, many different code paths and functions. So you need to figure out what is the code path that will allow you to reach the bug and whether that code path or another code path will make the bug exploitable. So after figuring that out, you need to turn this into a viable exploit. So it's very easy to crash the kernel, but whether you can turn the bug into something that gives you LPE is very difficult. So first, you need to think about bypassing kernel mitigations. So for people doing Google KCTF, that is experimental Google KCTF mitigations that you need to bypass. Or even if like you have a certain bug, you might want to get a better primitive. Like for example, for the chem inventory challenge, we wanted to get like kind of like a double free, which will allow us to like override pipe buff ops. So we want to get a better primitive. So after turning it into a viable exploit, another challenge that we usually face is to try to make the exploit reliable, because it's very easy to have an exploit that works 10% of the time, but it's not easy to have an exploit that works 99% of the time. Then we run the exploit and hopefully it works. Now, I think the new trend in like kernel exploitation is people want to write data-only exploits that work on different kernel versions. So if your exploit works on multiple different kernel versions and doesn't use a ROP chain, that is very nice. Yes, so kernel stuff is very cool. Finding exploiting 0 days or even like researching end days is also really cool. And I hope that you have enjoyed this. Thank you for having me. And if you guys have any questions, let me know. Are there any public write-ups for camp inventory? So, okay, camp inventory is actually a challenge written by me for Lag and Crash 4. There is one public write-up by Samu Zora. Yeah, so that is his write-up, and there's also my write-up, which is on the blog. Yeah. Is there a summarized mapping for the attack chain for the challenge? So, okay, so I'll just quickly summarize the attack chain. So basically find the vulnerability. The vulnerability is use after free by basically causing kmalloc to fail. And usually for these kind of heap bugs, what you want to do is you get a text leak and a heap leak first, and then think about how to control RIP or whether you want to go for a data-only exploit. So you determine what leaks you want. So in this case, what I would usually recommend is to like look at the vulnerable object. And if you look at the vulnerable object, you can see like what are the parts of the object that you can use to further your exploit. Like for example, does something possibly give you an arbitrary read, which in this case for the chemical object, the node address gives you an arbitrary read. Or is there something that you can potentially cause like arbitrary free? Like for example, in this chemical object, there's like a list thing going on. So if you can manipulate the linked list, you can get arbitrary free. So basically try to turn the primitive into something more useful and powerful. So after getting the text and heap leaks, you want to get RIP control. So now this is the point you decide whether you want to do a ROP chain kind of thing by like using certain structures like skbuff or pipe buffer object and override pipe buff ops to get RIP control, or you want to do a dirty pipe data only kind of thing. Yeah, so that's generally kind of like how the attack chain would work. Yeah. Yep. Does anyone have any other questions? Yeah, basically, just the thing is that for kernel land, because the attack surface is very big, you have a lot more flexibility in the kind of objects that you can use to help your exploitation. It's just that for kernel land, there's the whole cache thing going on, so you just need to be like very careful to see what objects are located in which caches and like what kind of attacks are blocked and what are not. Like, or whether you need to cross cache and that kind of thing. Like, so if you try to reallocate like kmalloc 256 to like kmalloc CG 4K, that would probably be bad because the order of the caches are different. Yeah, so it's that kind of thing. Yeah. What are the tools usually to search for kernel exploits? So if you're talking about publicly released kernel exploits, basically I would just say Google the CV number if you are looking to see whether there's an exploit for that CV, or you can just use like exploit DB or something. If you want to, I guess like if you want to write like custom kernel exploits, like a lot of this is like custom. So there are a lot of CTF challenges that you can practice with. Yeah, but generally in terms of tools, like kernel exploit is a very manual process, I would say. So yeah, if you're talking about finding kernel bugs, people use fuzzing. So there's like syscaller, Trinity, that kind of fuzzing tools. Yeah, I haven't personally had much luck with them, but a lot of people have good luck with syscaller and Trinity, but you do have to modify the fuzzers yourself. So that is one way you can find bugs. Or you can actually just do manual source code review, or you could use something like CodeQL. Camp inventory is considered what difficulty? For lag and crash, because that was polytechnic level CTF, that was considered quite hard. But I'll say like in terms of like hard CTF challenges, camp inventory is I wouldn't say it's the hardest kernel challenge. I've seen very cursed kernel challenges before. So I'll say probably like a medium in kernel. Yeah, hard will probably be all the weird like if you look at core CTF, they have these really cool obscure kernel challenges. Like those are like the goal. Yeah, so those are really cool but really hard. Yeah, but camp inventory, because it was written for a slight like a polytechnic level CTF, so not for university and above. It was one of the harder challenges in the event. Yeah. Why do I like cats? Because they're very cute. Yeah, cats are amazing. Do I have any tips for a beginner to learn binary exploitation? So for user land, there's actually this. I'll just send it. Let me just find this. So I personally learned Binex via this guy's stuff. So this is Pwn Nightmare by Guy in a Tuxedo. People also really like Pwn College. The nice thing about Pwn College is that they also talk about kernel exploitation. But when I first started learning kernel exploitation, I started using LK Midas' Introduction to Kernel Exploit. So maybe I'll send that as well. Yeah, so just slowly work through the different types of bugs and the different techniques. Again, the thing with binary exploitation is that there are so many techniques, so just like have fun and slowly learn it.
Thank you, Sherry. Is there anyone else who would like to ask a final question to Sherry? Okay, I guess there's no more question. So everyone that who attended this session, just to let you know, the recording will be available at M53 YouTube later. And thank you, Sharian. It's really insightful, and we learn heaps. And we keep discussing within our Discord about your challenges right now. And it's really interesting. Thank you for your time. We really appreciate it.
Thank you. Thanks for having me here. I've had a lot of fun preparing this actually. So I hope you guys enjoy it.
Thank you, everyone. I'm going to end the session in 1 minute.
Okay, thank you. Bye.